This is SpaceTime, Series 25, Episode 13, for broadcast on the 31st of January 2022. Coming up on SpaceTime, a mysterious celestial object unlike anything ever seen before, a black hole unlike any other, and the US Space Force launches 2 new spy satellites into orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered a mysterious new celestial phenomenon in our galactic neighbourhood that's unlike anything they've ever seen before. The object's thought to be a rotating neutron star or possibly a white dwarf, but it has an unusually powerful magnetic field, and it was emitting giant bursts of energy 3 to 4 times an hour. The study's lead author, Natasha Hurley-Walker from the Curtin University node of the International Center for Radio Astronomy Research, says the object was spinning around in space, sending out a beam of radiation which crosses the Earth's line of sight for 1 minute every 20 minutes, and it's one of the brightest radio sources in the sky. Even more fascinating, the object, which is in our galactic neighbourhood just 4,000 light years away, was appearing and disappearing over a few hours during the observations. When all these unusual characteristics are combined, there's simply nothing known in the sky that does this. The object was first detected using the Murchison Wide Field Array telescope in outback Western Australia. Objects that turn on and off are called transients, and they usually turn out to be either the death of a massive star or the activity of the remnants it leaves behind. Slow transients, like supernovae, might appear over the course of a few days and then disappear over several months, while fast transients, like rotating neutron stars called pulsars, can flash on and off within seconds, even milliseconds. But finding something that turns on for a full minute and then turns off for another 20 minutes, that's really weird. The source of the object was incredibly bright, but smaller than our Sun, emitting highly polarized radio waves, which all suggests that the object has an extremely strong magnetic field. Hurley-Walker says that matches a predicted astrophysical object called an ultra-long period magnetar, a highly magnetized, slowly spinning neutron star which so far has only been theoretical. Somehow it's converting magnetic energy into radio waves much more effectively than anything scientists have seen before. The authors are now keeping a regular check on that part of the sky with the Murchison Wide Field Array to see if it switches back on. If it does, telescopes across the southern hemisphere and in orbit will be brought in to observe it at different wavelengths. Hurley-Walker says the hunt's now also on for more of these objects in order to determine how common they are or whether this is rare and unique.
I'm using a radio telescope called the Murchison Wide Field Array to map the sky at radio frequencies. And this is building on some work I did about 5 years ago on the galactic and extragalactic all-sky MWA survey, or GLEAM. So we're doing GLEAM X, which is 10 times deeper, twice the resolution, and it's going to be amazing. But it takes a lot longer, and in doing the survey, we revisit the sky multiple times. So we look at the same spot and keep coming back to it. So we're building up all these images, and we're trying to make really deep observations of the sky. But I thought it would be a bit of a fun project to see what actually changes between the observations. Could we find things that were changing? And changing radio sources are called transients. So I gave this as a student project to an undergraduate, Tyrone O'Doherty, as his final year undergrad project. And so I gave him a little bit of code, some time on a supercomputer, and a lot of data. And I said, compare some observations and we'll see what changes. And he ran the code over about 24 hours of data that we took in 2018, split across about March and May, and covering the plane of our own Milky Way galaxy. And what a surprise, he found something. A source popped out of that data, something that was there in March and had completely disappeared by May. So this was super interesting because this source wasn't just switching on and then switching off across a couple of months, which is kind of what we were looking for, right? We were expecting sources that change really slowly, weeks to months to maybe even a year. But this source, when I looked into the data earlier this year, it wasn't just changing slowly. It was switching on and then off for 20 minutes and then back on again, and then off, and then back on again, and then off, and then back on again. So every 20 minutes. And that's just unprecedented because we don't know of anything in the universe that was expected to produce radio waves like that.
Yeah, normally when something switches on and off and on and off, it does it reasonably quickly, and we call those things pulsars. But this is different. This is 20 minutes.
Yeah, that's right. And the thing with pulsars is they're rotating so rapidly. You know, you've got the mass of a couple of solar masses, right, masses of the sun, squashed into a volume the size of a city. And just like a figure skater bringing their arms in to spin up on the ice, when a massive star collapses like that and forms a neutron star, that whole neutron star is rotating every few seconds. And it also compresses all of the magnetic fields of that massive star into this tiny space. And so that is just an enormously powerful engine that we've understood, you know, for about 50, 60 years. We've said, okay, we can do the math, we can write down pretty simple equations, and we can show how a rotating magnet like that in space can produce radio waves. But the thing with our source, which is only switching on and off every 20 minutes, if it's a rotating magnet in space that's going around at this kind of slow speed, you do the same math, and it just doesn't have enough energy to produce the radio waves. So that's a really interesting clue for astrophysicists. That's telling us that the radio waves aren't being generated by processes that we already know about. What we think might be happening is the magnetic field on this neutron star is quite strong, and it's getting twisted, it's getting complicated somehow. And as it untwists and relaxes, the energy is released as radio waves. And this sort of phenomenon is called a radiomagnetar. We actually know of a few radiomagnetars already. They rotate once every 1 to 10 seconds. But in theory, it's possible that you could have an ultra-long period magnetar. And that may be what we've detected.
Taking a step back now, we know it came into view, but then faded completely from view over a longer period of time. Is that because it's maybe in a binary system with something else, or it's now being hidden by something else?
So what we think is happening is just that it's an isolated neutron star, and its magnetic field got twisted like this. Potentially there might have been a starquake, you know, even like a little millimeter disruption on the surface of a neutron star releases an enormous amount of energy. And then the
I wish we knew what causes that.
Yeah, I know, right? So then the magnetic field has been untwisting and releasing these radio waves. But once it's untwisted, the source no longer has enough energy to generate radio waves. And so we think that explains why we found all of these detections in 2018, but we've looked all the way back to 2013 and there's nothing. And we've looked forward from 2018, 2019, 2020, 2021. I even did follow-up observations with one of the most sensitive radio telescopes in the entire world called Meerkat, and it's still not there in 2021. So it looks like this radio emission, these regular pulsations, were only there for a short period of time. And that kind of, that supports this magnetar hypothesis, that you need some complicated magnetic field that slowly untwists and releases the radio waves. So, of course, 18 minutes, yes, it does sound like potentially something could be in an orbit with an 18-minute period. The thing is, if you try and do the mathematics for that, then you can't have a normal star in an orbit like that, because a normal star would be too big. And if you had two stars like that, for instance, they would just smash into each other immediately. So you've ruled out normal stars. That means you've got to have compact objects like white dwarfs, neutron stars, or black holes. So you can put them in orbits with each other, that's fine, but then there's no real mechanism that can generate the radio emission that we're seeing. At least no one's put forward one in the literature so far. So that's why we are on the side of it being a rotating object rather than an orbiting object. And as for could it be something hiding behind something in an 18-minute orbit, and it's just producing this emission continuously, but then it's getting hidden? We don't think so, because if you imagine like the sun and Mercury going around the sun, you've got something very small, quite close in to something very big. It's only hidden for half of the time. So that doesn't work as a solution for why something would be visible for about a minute, then disappear for 19 minutes, and then come back again, and then go away again, and then come back and then go away again. It just doesn't add up as a solution.
What does this tell us about the structure of neutron stars, and in particular magnetars?
Well, what's interesting about this is, as I say, the radio that we're seeing is too bright to be explained by a kind of pulsar emission mechanism. You can't get the radio waves that we're seeing just from a normal rotating neutron star. It's spinning too slowly. So that does imply that the magnetic fields are twisted or they're being reconfigured somehow. And so we're going to have to adjust our models of how neutron stars work and what can occur on a neutron star in order to absorb this new information. Now, astronomy isn't all done by like one person. This work was a team effort, and there's quite a few of us on the paper from a few different institutions bringing different skills to the table. And most of us are observers. So we're used to looking at the sky, we see interesting phenomena, we take measurements, and then we publish them. There's a whole group of other astronomers called theorists, and they look at the reported observations and they say, okay, well, how can I adjust our models of the universe to incorporate the new observations? And that's really what I'm hoping will happen with this publication. We have a very small amount of information we can publish in one go, and I'm not a theorist, so I'm not going to be coming up with emission models for neutron stars and complicated magnetic field simulations, but there are people out there who will. And so I think over the next year, we're going to see a lot of thinking and a lot of publications drawing on this discovery. And that's where we'll start to get the understanding of what the source really is.
What happens now? You keep going back to that part of space, I guess, on a regular basis to see if this thing pops up again?
So we could monitor that position with the Murchison Wide Field Array, and we could just keep looking and see if it comes back. But the Murchison Wide Field Array can see 1,000 square degrees at a time. And in astronomy, you never just find one of a thing. Right? When we first saw the sun, we thought, well, there's only one sun. But then a little while later, people realized, oh no, the stars are also suns. The sun is a star. There's lots of stars where this is not a unique thing. When people first found pulsars, they named the first pulsar LGM1, Little Green Men 1, because they thought, well, a repeating radio signal, that must be aliens, and there's only going to be one. But then they found another one and another one and another one. They realized there's lots of these phenomena. So I think the same is going to be true with this source. We've found one, but there's going to be lots out there. And if we can observe 1,000 square degrees at a time, then we could be searching that 1,000 square degrees for sources all across the galaxy. So my plan this year is to put together a campaign where we search the galaxy on a sort of weekly to monthly basis, and we process that data really, really quickly. The source that we found in data taken in 2018. We only made the detection in 2020, and we only wrote it up and published it in 2021. That's a 3-year lead time. That's no good if you're trying to look for sources that appear and disappear. So what I want to do is shorten that time to just 24 hours. I want to be able to look at the whole galaxy, find things that are changing, and report them immediately. And that will allow telescopes all across the world, in space, to all point towards that location. And that's how we're really going to understand what these sources are.
That's pretty much the same way they determined what gamma ray bursts were.
That's right. Gamma ray bursts, fast radio bursts. It all depends on being able to get to a source quickly and track it with as many telescopes as you can find. And so that's the aim. Of course, I don't do this in a vacuum. I'm working with lots of students and postdocs and colleagues to try and set this up. And I'm going to be seeking funding in order to actually get the project off the ground. And this is where basic science funding goes, right? Not everything has an immediate application, but exploring the universe and kind of finding entirely new, unexpected discoveries, well, I think it's an important thing. So I'm going to be trying to seek funding to support the project.
That's Dr. Natasha Hurley-Walker from the Curtin University node of the International Centre for Radio Astronomy Research. And this is SpaceTime. Still to come, a black hole unlike any other, and the first Russian spacewalk for 2022. All that and more still to come on SpaceTime. Astronomers have discovered a black hole unlike any other, hidden at the heart of a globular cluster in our nearest big neighbouring galaxy, Andromeda M31. At 100,000 solar masses, the object's a lot smaller than supermassive black holes found at the centres of galaxies, but also far larger than stellar mass black holes, which are born out of the death of massive stars. The globular cluster, catalogued as B023-G078, is a good example of why many astronomers now believe that at least some globular clusters are the stripped-out nuclei of smaller galaxies cannibalized by larger ones, rather than large groups of stars bound together by gravity, which were all originally born together in the same molecular gas and dust cloud within a galaxy. Astronomers have made good confirmed detections of stellar mass black holes up to 100 times the mass of our Sun. And supermassive black holes at the centres of galaxies are usually millions to billions of times the Sun's mass. But there still aren't many observations or measurements of true intermediate-sized black holes, those which have masses ranging from several hundred to many thousands of times that of the Sun. The unusual mass of this object, which is reported in the Astrophysical Journal, makes the discovery one of only a handful of confirmed intermediate mass black holes, objects which have long been sought after by astronomers. One of the study's authors, Anil Seth from the University of Utah, says the new discovery fills an important gap in the evolution of black holes. The globular cluster B023G078 was known to be one of the most massive objects in Andromeda. However, there's only been a single observation of the cluster, which determined that it had an overall mass of 6.2 million solar masses. Now, that's a lot for a stellar cluster, but not for a stripped-down galactic nucleus. The new observations, using the Gemini Observatory and the Hubble Space Telescope, allowed the authors to calculate how the mass was distributed within the cluster by modelling its light profile. See, a globular cluster has a signature light profile that is the same shape near the centre as it does in the outer regions. But B023G078 is different. The light at the centre is round but then gets flatter moving outwards. And the chemical makeup of the stars in the cluster changes well, with more heavy elements near the star's centre compared to those near the object's edge. And as we mentioned earlier, stars in globular clusters usually form at the same time, which is very different from stars in stripped galactic nuclei, which have repeated formation episodes, where gas falls into the centre of the galaxy and forms new stars. Also, with galactic nuclei, other star clusters can get dragged into the centre by the gravitational forces of the galaxy, and that makes these nuclei sort of like cosmic dumping grounds for a bunch of different stuff. So, stars in stripped galactic nuclei will become far more complicated than what's found in globular clusters. And that's exactly what the authors are seeing in B023G078. The authors then used the object's mass distribution to predict how fast the stars should be moving at any given location within the cluster and compared that to their actual observations. They found the highest velocity stars were orbiting around the centre. But when they built a model without including a black hole, the stars at the centre were too slow compared to their observations. But once they added a black hole to their calculations, their stellar velocities began to match the data. The black hole adds to the evidence that this object is indeed a stripped-down galactic nucleus. That's because astronomers think it's difficult for globular clusters to form big black holes. But if it is a stripped galactic nuclei, then there must already be a black hole present, left as a remnant from the smaller galaxy as it merged into the bigger one. The authors are now searching for more stripped galactic nuclei which may hold intermediate mass black holes. That's because it's an opportunity to learn more about the black hole population at the centre of low-mass galaxies and about how big galaxies are built up by cannibalizing smaller ones. This is SpaceTime. Still to come, the first Russian spacewalk for 2022, and the United States Space Force launches 2 new spy satellites. All that and more still to come on SpaceTime. Russian cosmonauts aboard the International Space Station have completed a 7-hour spacewalk to finish integration work on the new Nauka multipurpose laboratory module and Prichal docking port. The two components were attached to the Russian segment of the orbiting outpost on separate flights in July and November last year. During what was the first spacewalk for 2022, the cosmonauts installed handrails, rendezvous antennae, closed-circuit television cameras and docking targets onto Prichal, which will provide airlocks and docking facilities for visiting Russian spacecraft. You may recall Nauka's arrival in July last year was far more noteworthy than desired, after faulty software on the module unexpectedly fired up the thrusters 2 hours after docking, spinning the entire space station out of control. The problem was only resolved once Nauka finally ran out of propellant. This is SpaceTime. Still to come. The United States Space Force launches 2 new spy satellites, and later in the science report, a new study has shown that people suffering from paranoia are also more likely to believe in conspiracy theories. All that and more still to come on SpaceTime. The United Launch Alliance has successfully placed a pair of spacecraft tracking spy satellites into orbit for the United States Space Force. The mission, aboard an Atlas Centaur rocket in an unusual 551 configuration, was launched into cloudy skies from Pad 41 at the Cape Canaveral Space Force Station in Florida. The Atlas V launch vehicle was equipped with an additional strap-on solid rocket booster for the mission.
ULA's Atlas V 511 rocket, the first and only planned mission using this configuration, is launching USSF-8. This is the 91st Atlas V launch and ULA's 140th launch. Built in ULA's 1.6 million square foot production facility in Decatur, Alabama, the Atlas V Common Core booster is powered by an NPO Energomash RD-180 engine and a single Northrop Grumman solid rocket booster to provide additional thrust at liftoff. The Centaur second stage is powered by an Aerojet Rocketdyne RL-10 engine. The 2 spacecraft are encapsulated in a 5-meter diameter RUAG payload fairing. These rocket components travel from Alabama to Cape Canaveral on ULA's rocket ship.
USSF-8 will launch 2 identical Space Situational Awareness Program satellites, GSAP-5 and 6, to a near geosynchronous orbit, approximately 22,300 miles or 36,000 kilometers above the equator. GSAP is a space-based capability that collects space situational awareness data, allowing for more accurate tracking and characterization of human-made orbiting objects. The satellites have unobstructed and distinct vantage points for viewing resident space objects orbiting Earth, without the weather or atmospheric disruptions that limit ground-based observations. This will be the 3rd launch for the GSAP program, following the successful 2014 and 2016 launches of AFSpace 4 and 6, which both launched atop Delta IV rockets. USSF-8 will be the first flight of the Atlas V 511 configuration.
I'm here at the Vertical Integration Facility at Space Launch Complex 41. Behind me, the team is preparing to move the Mobile Launch Platform, or MLP, to the pad. Before we do that, here's a look at how the rocket was stacked. Our process began with lifting the 107-foot or 33-meter booster onto the MLP. Then the team mated the SRB to the booster, followed by the transport and lift of the Centaur into position. Finally, the payload fairing, with both spacecraft already encapsulated, was mated to the Atlas V rocket. Once the rocket is fully assembled, we start the countdown procedure by moving the Mobile Launch Platform from the Vertical Integration Facility to the pad. To complete this move, 6 components are used for the 20-minute trip to pad, which spans about 1/3 of a mile. The MLP weighs approximately 2 million pounds, supports the rocket, and contains air conditioning, electrical, and commodities lines. The undercarriages bear the weight of the MLP and the rocket. Additionally, 2 rail cars lead the move, with the payload van providing spacecraft communication and the ground van providing support for the rocket. At the rear of the convoy is an environmental control system providing air conditioning to the payload and rocket, and trackmobiles power the nearly 3 million pound convoy. The Atlas V rocket stands 196 feet, or about 60 meters, and weighs 775,000 pounds, or more than 350,000 kilograms, fully fueled. With the rocket on the pad, the launch team then transitions to fueling and other final preparations.
ULA's Atlas V 511 rocket is launching both GSSAP spacecraft to near geosynchronous orbit. Let's learn more about today's flight.
Liftoff of the United Launch Alliance Atlas V rocket.
The RD-180 main engine and one solid rocket booster ignite to lift the Atlas V rocket away from the pad. Together, the main engine and single SRB generate a combined liftoff thrust of 1.2 million pounds, or 5.3 meganewtons. Shortly after liftoff, Atlas begins a pitchover to attain the proper flight path while minimizing the dynamic pressure the vehicle experiences during flight. The Atlas V reaches Mach 1, the speed of sound, at 58 seconds. 2 minutes into flight, the GEM 63 solid rocket booster is jettisoned. During ascent, the spacecraft are protected inside a 5-meter diameter payload fairing. At approximately 3 minutes 30 seconds, the rocket has climbed above the densest part of Earth's atmosphere, and the payload fairing is jettisoned. At 4 minutes 21 seconds, propellant levels are depleted and the main engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs a little more than 5% of what it did at liftoff. At 4 minutes 37 seconds, the first Centaur main engine burn begins. Over the span of more than 6.5 hours, Centaur's RL-10 main engine will perform 3 engine burns. Approximately 6 hours, 31 minutes after liftoff, the RL-10 engine ignites for a final burn. This burn enables Centaur to make a plane change towards its geosynchronous separation orbit. Nearly 2 minutes later, Centaur completes its final engine cutoff, following a guidance-commanded shutdown, a capability which ensures precise orbit injection. 6 hours, 35 minutes, 48 seconds after liftoff, Centaur releases the first satellite, followed by the second satellite approximately 10 minutes later. The Space Force's identical geosynchronous Space Situational Awareness Program satellites then continue their journey to geosynchronous orbit.
Status check to proceed with terminal count. Atlas Systems, propulsion. Go. Hydraulic. Go. Pneumatic. Go. LO2.
Go.
Water.
Go.
Centaur Systems, propulsion. Go. Pneumatic. Go. LO2. Go. LH2.
Go.
Gas. Go. Electrical systems, airborne. Go. Flight control.
Go.
Comm.
Go.
Umbilical.
Go.
ULA safety officer.
Go.
Vehicle systems engineer. Go. Range coordinator. Clear to proceed. Launch director.
Launch vehicle is ready to launch.
Mission director.
You have permission to launch.
Proceeding with the count. ALC verified T0 set for 1900 Zulu. Verified.
Polling is complete. The ULA launch team and the Space Force mission director are go for launch.
LC spacecraft going internal.
Roger.
Atlas tanks to flight pressure. LC spacecraft internal.
Roger.
Vehicle internal. Launch sequencer start.
Securing Centaur LH2.
Securing Centaur LO2. Launch enabled. FTS arm.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
Range green.
Status check.
Go Atlas.
Go boost Centaur. Go USSF-8. ECDS reduced for launch.
10, 9, 8, 7, 6, 5, 4, 3. We have ignition. And liftoff of the United Launch Alliance Atlas V rocket carrying SF-8 for the United States Space Force.
Now 10 seconds into flight, vehicles begun the pitch over maneuver. Body response look good.
You're now hearing the voice of Patrick Moore providing launch vehicle ascent data.
Now 20 seconds in. RD-180 propellant utilization system has gone to closed loop control system. Response looks good. Now passing 30 seconds into flight. Vehicles completing the pitch over maneuver. Body rate responses continue to look good. Engine operating parameters continue to look good. SRB chamber pressure within expected ranges. Now coming up on 58 seconds into flight. Mach 1 Atlas 5 is now supersonic. RD-180 engine operating parameters continue to look good. SRB chamber pressure looks good. Now passing through max Q, maximum dynamic pressure. Now passing 1 minute 30 seconds into flight. SRB chamber pressure tailing off now as SRBs are burning out. And we have SRB burnout. RD-180 throttling down slightly as expected. Engine response looks good. Body rates continue to look good throughout boost phase. RD-180 engine operating parameters continue to look good. Now 2 minutes into flight, we have good indication of jettison of the SRB. The Atlas V now weighs 1/2 of its liftoff weight. And the vehicle has gone to closed loop steering. Body rates look good. Atlas V is now 38 miles in altitude, 35 miles downrange distance, traveling at 4,200 miles per hour. RD-180 pump speeds and injector pressures continue to look good. Body rates continuing to look good throughout boost phase. And Centaur reaction control system is now pressurizing to flight levels. RD-180 now throttling down to maintain a constant 2.5 G acceleration limit. Engine response looks good as it's maintaining that 2.5 G acceleration limit and standing by for payload fairing jettison. And we have good indication of payload fairing jettison. And we have CFLR jettison. And RD-180 now throttling to maintain a constant 4.6 G acceleration limit. And we've begun boost phase chill down and standing by for booster engine cutoff shortly. And we have BECO booster engine cutoff standing by for stage set. We have good indication of Atlas Centaur separation. We have pre-start on the RL-10. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good. And this first burn of today's mission will last approximately 8.5 minutes. Centaur's gone to closed-loop steering, body rates continue to look good, and the RCS system has begun initial thruster firings for thermal conditioning as expected.
The first of the two spy satellites, GSS-AP-5, was deployed 6 hours and 35 minutes after launch. It was followed 10 minutes later by the second spacecraft, GSS-AP-6. The classified satellites are joining 4 similar spacecraft, which are designed to detect, study and track spacecraft in geosynchronous orbit. Built by Northrop Grumman, the Geosynchronous Space Situational Awareness Program satellites are designed to undertake rendezvous and proximity operations, maneuvering close to a target spacecraft and collecting as much data about it as they can. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study has confirmed that taking a COVID booster shot that was different from your first and second dose appears to result in a stronger antibody response. The findings, reported in the New England Journal of Medicine, follows a study involving 3 booster shots, Pfizer, Moderna and Johnson & Johnson, which is similar to AstraZeneca, with about 150 participants receiving each booster. All combinations boosted neutralizing antibodies, but there was a stronger response from those who mixed and matched their vaccines. T-cell responses also increased for every group, except those who had Johnson & Johnson only. Over 5.6 million people have now been killed by the COVID-19 coronavirus since it first spread out of Wuhan, China. However, the World Health Organization says the true death toll is likely to be at least double that amount, with almost 360 million confirmed cases. A new study has shown that people who are paranoid are more likely than others to believe in conspiracy theories, including anti-vax beliefs. The findings, reported in the Journal of the Royal Society Open Science, are based on a study of 1,000 people which showed that those who scored high for paranoia were also more likely to believe any conspiracy theories they were presented with, especially those theories that suggested sinister forces were intentionally causing harm to society or to the individual in question. And believing in one conspiracy theory also meant people were more likely to believe others. Overall, taking the whole group of respondents into account, people are more likely to believe theories that suggested that harm was caused accidentally rather than intentionally, and that these harms affect society as a whole rather than just a specific individual. A new study has found that kids' school shoes should be soft and flexible, not hard and supportive. Scientists from the University of Sydney found that school shoes that allowed more natural movement had the most positive impact on kids' foot strength, muscle structure, and balance as they grow. Previous research had shown the benefits of kids going barefoot, but this wasn't an option for school. The randomized controlled trial, reported in the journal Gait and Posture, involved 70 school kids aged 9 to 12 wearing either a standard or a moderately minimalist school shoe at least 3 days a week over a 9-month period. The standard or control shoe was characterized by a polyurethane sole with leather uppers and laces. The minimalist shoe had a softer shock-absorbing sole, with the upper made of a combination of textile, elasticized base and suede panels. The author saw significant improvements in balance in kids who wore the more minimalist shoe, and these improvements were linked to small improvements in toe flexure, strength, and muscle size. A new study has found that young people in Canada are far more likely to believe in pseudosciences like astrology than the rest of the population. The findings by Research Co. and Glacier Media sought to learn more about the way Canadians feel about pseudoscience and the paranormal. Tim Mendham from Australian Skeptics says subjects were questioned about their views on a range of supernatural beliefs.
A research company in Canada asked about 1,000 adults on their belief in astrology, mediumship, clairvoyance and haunted houses. And they're looking at it from two angles. One is sort of just do you believe it, and two, do you act upon it? Or act because of it, especially as regards astrology. And most of the story was associated with astrology because the beliefs were scattered and widely diverse amongst the people they asked. The older you were, apparently, the less likely you are to believe in astrology. The thing that fascinated them was that, say, young people, 18 years and up to mid-30s or something, more than half of them believed in astrology. Now, the issue is that they believe in astrology. About 25% or so of young adults also looked at astrological charts and astrological predictions and things fairly regularly. So not just believe, they actually sort of followed it up a bit. And that's more than the average person. In fact, belief amongst older adults has been decreasing over the years, but belief in by these young people has been increasing recently. It does go up and down compared with the belief in the other topics they looked at, mediumship, clairvoyance and haunted houses. They were pretty stagnant and hadn't moved very much and were fairly low, certainly compared to astrology. But it's interesting that young people, and it's another aspect of this, they found people in the west of Canada were more likely to believe than people in the east. So if you're a young person in the west of Canada, you're probably more likely to believe, a lot more likely to believe in astrology than an older person in the east of Canada. So it's just some of the interesting quirks you get when you're sort of digging through research and doing studies. Now, is 1,000 people enough? Yeah, that's a good start. The fact that they looked at these two questions of belief and then close impact, if you like, of that belief is an interesting thing to look at. More people believe than actually take it seriously enough to follow it closely. So, but even so, if the young people are believing in it more than older people, why? That's the $64 question, isn't it, as to why exactly that's happening. Naive, disenchanted with religion, so they're turning to other, quote, religions, close quote, all sorts of things. I mean, you think younger people are more exposed to a lot of beliefs now through social media, etc., but they also mean they're exposed to a lot of more factual information and non-factual. So it's a hard one to figure out, asking why rather than just what people believe in. That's the thing that the skeptics love to know about, actually the why, and there's all sorts of speculation, as you say. Are they less knowledgeable? Are they more open to things? Are they sort of more naive? Who knows? Are they less cynical, if you like, or have they just not experienced how astrology doesn't work, which it doesn't. Perhaps astrology is more exciting than other systems that will determine your future, like what you actually do. Anyway.
Failing in the education system, maybe.
It's a mixture of things. That definitely, I would say, is quite a strong possibility. It's an anti-science movement, and if science says astrology doesn't work, people think, well, science is a lot of hokum, and we look at other things. They always say that in periods of panic and concern and stress, people tend to believe more in a lot of these sort of paranormal and pseudoscientific areas than they would if life is going on very nicely. Obviously, we're in a period of stress right now, so that might help to increase belief. But it should increase belief by all people, not just young people. But obviously, the young people are more concerned or more interested in such things than older people.
Young people haven't got the wisdom of age, so they're more gullible.
It sounded like Oscar Wilde there, who said that youth is wasted on the young.
I thank you for that. It makes me sound much more intelligent than I actually am.
Yeah, me too.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.